So what is there inside a permanent magnet? You know, due to a permanent magnet, first we'll see if there is a permanent magnet, so there is a magnetic field outside. At least the field outside we know is of this nature, like this. See, through inside also the fields will pass like this. Through inside the magnet also the fields will pass like this. Now question comes, why the field will pass through this inside? But in an electric dipole what happens if there is a plus q charge and a minus q charge? See, what are the electric lines of force? It's, see, for the outside point it is quite similar to magnetic lines of force, but here the electric lines of force between the charges is from plus charge to minus charge. The reason is that, see, this plus charge can be thought of a source of electric flux, and this minus charge can be thought of a sink of electric flux. So see, across this, this integration of E dot dA is equal to q by epsilon naught. But in case of magnetic field, integration of B dot dA is always equal to 0, as monopoles are not found in nature. Monopoles are not found in nature. So there cannot be any such source of magnetic fields lines like that, source or sink, whatever. Okay, so we think that this is a plus pole, plus m strength, this is minus m, but in reality, if you consider an area here like this, so across this integration of B dot dA is equal to 0. So these are the magnetic lines of force near a bar magnet. Now, and this is a permanent magnet. Now the question comes that what makes the magnetic lines of force like this near a bar magnet? We know it's true for a solenoid. If you have a solenoid, so the case reminds us of a solenoid. If you have a current carrying coil like this solenoid, then what happens? Say current flows through this solenoid, then the electric lines of force are there like this. And if you look at the lines of force, so this also goes like this, bends. Okay, so if you compare the solenoid with the bar magnet and the lines of force, it is exactly same. It is exactly similar. So there, so where come the solenoid comes here inside this bar magnet? Where do you get a solenoid inside the bar magnet? There is no current carrying source as such. I mean, we can't really see any current carrying source, right? So what happens here? Actually, every atom has got a magnetic moment. So every atom, see, not all atoms. So the atoms having unpaired electrons, have a magnetic moment. That means it is equivalent. It is equivalent to a current carrying coil. So for simplicity, let's look at the hydrogen atom. So this is the nucleus of the hydrogen atom, that is the proton, and this is the electron revolving, suppose, in a circular orbit. So this is having minus charge, this is the direction of revolution of the electron. Now the electron revolving in this way, that means, so that is equivalent to having a current this way, right? So the electron revolving in this way in the clockwise direction is equivalent to having a current. And suppose this is the radius of the atom, or we call this r is the atomic radius. So I multiplied by pi r square is what? It is mu a. Mu a stands for the atomic magnetic moment. The atomic magnetic moment. So this is a simple model for a hydrogen atom. Now there are certain certain substances known as ferromagnetic substances. Inside ferromagnetic substance, what happens inside a permanent magnet in a ferromagnetic substance? I will show you what happens. How it happens, that is different question, but what happens, I will show you why it behaves like a bar magnet. Now, so all the atoms are aligned in a particular direction. Not all, I mean almost, or sorry, we can say most of the atoms. Most atoms are aligned in a particular direction. So that all the magnetic moments, let's take a hypothetical case, let's take 100% atoms. So all the the atomic magnetic moments are in a particular direction. Let's take this hypothetical case. Suppose it happens. So all the atomic moments, magnetic moments, so these are the atoms. This is just the front part. And throughout you have these atoms, right? Throughout you have these atoms. Throughout you have an atom here, have an atom here, have an atom here, here and here, throughout like this. Okay. Now in each atom, the atomic magnetic moments are pointing in a certain direction. So suppose this is the direction in which the atomic magnetic moment, what is that? It is denoted by mu a. So it's all atomic magnetic moments in a particular direction, this way, mu a. That means these are the atomic currents. This current like this, current like this. Now if I look at the front view of this thing, I see these are the current carrying coils. There are many in number, but for simplicity and for my own convenience and limited capabilities, I am drawing a few of them. So the thing is like this. Now you see that. Now here in this region, say in this region here, okay, this region, what happens? This region, okay, this region, and to some extent in this region also. This goes this way, this goes this way. So in this region also. So the currents actually cancel each other, because see, if you see in this region, say one current goes up and one goes down, so that is equivalent to no current. And in this region also, one goes towards right and the lower one goes towards left, so this is also equivalent to no current, zero current. So actually in total effect, what current do you have? you have only the surface current. All the other currents vanish because they cancel each other. So due to this atom, you have these surface currents. Now in a diagram I will show you. So these are the directions of current. These are the directions of current, and in the net effect, you have this current. Right? Current over the surface of the solid. Current on the surface of the substance, like this. So this is also this is like a solenoid, right? This is like a solenoid. So even if you see this left picture also, there are these solenoids like this. These are very very thin solenoids. So there are many of them. So obviously in a solenoid, you have these magnetic lines of force. Magnetic field rather, not lines of force. Magnetic field lines. So here through all these solenoids you have this magnetic field lines B. You can justify it from here also, this diagram also. So there exists this magnetic field lines B. So this is solely due to the atomic current. So here you have IA. Here also this current actually is IA in each of these atoms. Now suppose say, so IA is the atomic current and alpha A is the atomic cross section, the cross section of each atom. So and suppose N, so N is total number of atoms in the ferromagnetic this magnet or this sample rather, ferromagnetic sample or the bar magnet rather. Bar magnets are made of ferromagnetic substance. So in ferromagnetic substance you have this, all the atoms may have this magnetic moment, all aligned in a particular directions. In other substances you don't have this. So they are gifted with this nature, and you have to use some external magnetic field also. So here say each of these magnetic moments, say this is IA, so this is mu A. So in ferromagnetic what happens? In ferromagnetics there are domains. Domains means groups of atomic magnets. Those are oriented in a particular direction. Now, why they are oriented, it needs to study quantum physics. It is such a subject of physics that Professor Shankar says that he is one of the greatest professors of quantum physics. Those who know quantum physics know that they don't know quantum physics. They are absolutely convinced that they don't know quantum physics. So we will not deal with quantum physics. So we'll just know that the ferromagnetics are born with such properties. such that here there this certain magnetic moment, there these arrows corresponding to this mu a, they are aligned in certain direction. This is the domain, and a certain group are aligned in this direction, another group aligned in this direction, and maybe aligned in this direction, and so on. These are the domains. Now what happens? So in presence of external magnetic field, in presence of external magnetic field, call it B external, BEXT, B external, what happens? The domains say arrange themselves in a particular direction, obviously. So some external force is needed, or some external torque is needed on the magnet. So how it's supplied, I'll show you. So the external magnet, say if you keep this ferromagnetic inside a solenoid, this current carrying coil, now what happens? So it produces a reasonably strong magnetic field B external, so that due to this B external, in direction of B external, the magnets will try to point, because that is the most stable configuration. When you have a magnetic moment mu a, be it an atomic magnet or a bar magnet, and you have this B external, the magnet is most stable when it is parallel to B external. So what happens? There is such a condition when almost all the atoms, they are arranged in a particular direction. So it's this thing only which happens, the three-dimensional view. So these are the things, these are the atomic magnets, and they are so these are the solenoids. These are solenoids made by atomic currents. I hope you followed what I am trying to show. Very difficult diagram to draw. That is the best I have tried out. That is the best I could do. So that's mu a due to each. Okay. Now, so this, so when the atoms are arranged, or when the domains are arranged, then let B atomic be magnetic field inside the ferromagnetic due to atomic magnets, right? Now, so B atomic is equal to how much? It's mu 0 n into I atomic. What is n? N is number of atoms per unit volume, or number of turns. So turns is atom, right? So each turn is an atom. Number of atoms in unit volume. Okay. So here you remember that this n is total number of atoms. So n is there number of, no, I've written it wrong actually. Number of atoms in unit length. Number of atoms in unit length, not number of atoms in unit volume. In unit length, sorry. Okay. Total number of atoms. And if I draw this one, there let's draw a solenoid. This one, the solenoid, there are billions, millions of these solenoids. I'm drawing one of those. So for this solenoid, this is a cross section area. This is the cross section area, and suppose this is the length. Okay, now say this is the length. I mean, this is the length of the bar magnet. Okay, so this n is total number of atoms. So here in this solenoid, this is B external, B atomic, the atomic magnetic moment. So B atomic is equal to mu 0. Okay, so number of atoms. Okay, now suppose say NV. So if NV is number of atoms in unit volume of ferromagnetic. Now so this mu 0 NIA, right? So we can again write B atomic is mu 0. Okay, so what is the volume of this atomic solenoid? So for the atomic solenoid, for this atomic solenoid, the volume is equal to L multiplied by alpha A. Okay, so that is NV, N multiplied by alpha A, right, divided by L. Got the point? Multiplied by IA. See, N is number of atoms, so it is atoms by length. Okay, so that means it is atoms into alpha A. So it is atoms per unit volume. This one is atoms divided by volume. So that is NV multiplied by alpha A. That is what you get here, divided by length. So therefore B atomic is equal to mu 0 NV alpha A IA. Okay, so atomic happened to be mu 0 NV IA alpha A. So IA into alpha A is mu A. Mu A is the atomic magnetic moment. Atomic magnetic moment. Now, so NV into mu A is this NV is number of atoms by volume. Atoms divided by volume, and this is magnetic moment per unit atom, per atom. So you get this quantity is magnetic moment per unit volume, as this is magnetic moment mu A multiplied by number of atoms per unit volume. Mu A is magnetic moment of a single atom multiplied by atoms per unit volume. So this is magnetic moment per unit volume. This is known as so this is denoted by I, and it is known as intensity of magnetization. Intensity of magnetization. So this B atomic happens to be mu 0 times I. Now let's go inside this bar magnet. So the field inside the bar magnet was induced by B external. After being induced by B external, you have a field inside, it goes through, that is B atomic. So inside ferromagnetic, the net magnetic field inside the ferromagnetic, the net magnetic field happens to be B is equal to B atomic plus B external. Actually, you will be surprised to know that this B external is much higher. This B atomic is much higher than B external. B external is nothing when compared to B atomic. And so that is why B atomic for ferromagnetic is much greater than B external. And this B external is brought in by a solenoid, suppose. Right? This is B external. You write it as mu 0 into H. Now this H is known as the magnetizing field. Its unit is equal to, obviously you know, mu 0 into H. So it is ampere per meter. Ampere into meter inverse. Even intensity of magnetization has same unit of ampere per meter. So therefore, resultant field is equal to B atomic plus B external. That is, B atomic is equal to mu 0 I plus this is mu 0 H. So B is equal to mu 0 times I plus H. So here, for the ferromagnetic, we can draw a curve of H versus I, or I versus H rather. This is known as the hysteresis curve, magnetic hysteresis curve. Okay. Now suppose you have a ferromagnetic substance, domains are like this, randomly arranged, so it is completely demagnetized. I mean, the state before any external field is applied. Now the external field is applied, so external field means actually H, you know, B external equal to mu 0 H, and B atomic is equal to mu 0 I. So if you apply the external field, now gradually when all the atoms are aligned almost, then it attains a saturation state. And from this saturation, so this spot is known as a saturation state. Now from saturation state, what happens? You suppose you remove the external magnetic field, still it remains a permanent magnet, right? Its whole magnetism is not lost. It still remains a magnet. So the curve, instead of tracing back the same curve, it goes like this. So this thing is the retained magnetism, right? And this distance along the I-axis is the retained magnetism. It shows the retentivity. So now, if I want to demagnetize it completely, then I have to apply the external magnetic field in the opposite direction. So that is why when you go like this, then so the atomic magnetism is 0. So this distance signifies the coercive force. Coercive force means the opposing force to demagnetize the magnet completely. Now this curve goes on again like this. So you attain a saturation in this direction, So to the right it has this north pole here and south pole here. To the left it has north pole here and south pole here. It attains saturation. And again you want to say, again you bring the external magnetic field to 0. It retains some magnetism, and again demagnetize it, come here, and again like this. So the area under this hysteresis curve, this total area, it signifies the heat generated in magnetization and demagnetization of the substance. So in this lecture up to this only. Later on we'll study about magnetic susceptibility and paramagnetic and diamagnetic substances.